All right, let's talk about habitat data and the processes involved in creating these types of maps. Habitat is something we talk a lot about in natural resources. It's the environment of a critter, which can be, a plant, an animal, or even you. Habitat is the space that provides food, water, shelter, and location to survive. We talk about habitat suitability a lot in natural resources, but keep in mind that suitability modeling applies to any situation in which we want to map specific locations that meet our needs. Where's the best location for a new hospital in a growing community, for example? Habitat data that we can access from various sources is typically vector-based polygons like you see here, and often includes seasonal ranges. So the question is, how are these maps created? There are two general methods for constructing habitats or home range maps. The first method builds from knowing what the critter needs to survive. These are environmental preferences or landscape characteristics. If we're trying to identify communities that are underserved by access to emergency care, we might look at criteria like distance from existing hospitals, population distributions, and road networks. Each input criteria is a map layer that represents suitability. The layers are overlaid and combined to identify areas that meet the suitability standards. Inductive models are built using known locations. Locations can come from radio collar data, geotagged photos, or GPS or cell phone data. We can use the known locations to create a density surface and extract the landscape characteristics within the highest density areas. So deductive models are based on known landscape characteristics. This can come from literature or understanding of the species. It combines different map layers to identify suitable locations. And inductive models are based on known locations, radio collar data. If we look at the workflow as a flow chart, it goes like this. Start with the landscape characteristics needed or preferred. In this example, our critter needs clean air, pockets of warm sun, and access to food. The map layers we need then will include air quality, sun, which could mean solar radiation, hours of daylight, aspect, or the direction a slope is facing. And access to food might mean a specific vegetation type, proximity to lakes or streams, or walkability to a grocery store. We're going to normalize the data, which means we're going to control for different units of measure, which is going to create bias in weighting the values. So we're going to normalize, and I'll talk about that in just a second. And then we're going to combine the input map layers using a raster calculation and map the resulting ideal habitat locations. So this is an example using the model builder in ArcGIS. The model can be saved as a tool for workflows that you execute often. So let's take a look at this workflow in a little bit more detail. This is a representation of the workflow going on behind the curtain of Esri's suitability modeler. The desired outcome is a map of areas that meet a set of input criteria. So first we need to define our goal. If we want to determine potential habitat corridors, we might combine map layers of suitable slope, land cover, consider barriers, and other characteristics that would aid or impede movement from one habitat area to another. We're going to derive secondary data. For example, calculate a slope surface from elevation. And using stream polylines, we could calculate a raster surface where the cell values equal the distance from that cell to the nearest stream feature. The transformation is the important part. What we've done here with slope is think about what are the most suitable slopes for our bobcat habitat, and then we are assigning it a value of suitable to unsuitable, and it could be a binary or a range of suitability. Land use, same thing. Whatever the most common or preferred land uses are, we're ranking, creating a classified set of values that's ranked from suitability or suitable to unsuitable. Then we can weight these values and combine them to locate the final sighting areas. So let's look closer at the data and talk about some of the details that are important to this process. For this last example, the suitable sites we want to map must be far from roads, have lower elevations, and low slope. So first we calculate a raster layer that maps the distances of each cell to the nearest road feature, like I mentioned in the last example. This is done using the Euclidean distance tool. The rasters will have ranges of values like these: 0 to 8,000 for road distance, 1,400 to 2,800 elevation, and 0 to 85 slope. We know the units for these are meters, and degrees for the slope, but the model is only going to consider the values when adding them together. So we aren't going to add these raw input values together. The perceived difference between 0 and 90 degrees of slope is extreme. It's from flat to vertical, and yet the range is only quote-unquote 90. 90 relative to the value ranges for elevation or road distance is completely insignificant. So we're going to be biasing and underrepresenting slope changes if we use the raw values. So the input values need to be normalized to control for differing units of measure. And the easiest way to do that is to classify the ranges of values into levels of suitability. So our base layers are the roads and elevation. From this, we'll derive our secondary surfaces, distance to nearest roads, which is a raster output where each cell value contains the distance from that cell to the nearest road segment, and slope, which is calculated from the elevation model. Normalizing the value ranges comes in the next step, reclassifying. The most basic normalization would be to assign the input values into one of two categories, suitable or unsuitable. This creates a binary or true-false classification system. Raster cells that are suitably far from a road are assigned a suitable value of 1, and cells closer to roads are assigned the false value of 0 or unsuitable. The reclassify tool replaces the distance to road value with a 1 or a 0. The same process is used to simplify the slope layer. The cells containing low slope values are all assigned a new value of 1, and cells with high slope values are replaced with new values of 0. Elevation cells are reclassified into low or suitable cells with a value equal to 1, and high elevation cells are assigned 0. In this example, I've manually changed the color of suitable cells to green and unsuitable to some kind of a bluish hue. And that's just so that I can keep track and verify my results as I'm working through the model. In the last step, the plus tool, or the raster calculator, which does math on raster layers, is used to add the three inputs together. So what do you think the range of output values will be if we add these three inputs together? If you guessed 0 to 3, ding, 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 you are correct. Again, here I've manually symbolized the most suitable cells using green. These are cells with a value of 3, which means that all three input criteria are suitable in that location. The darker green is mapping cells with a value of 2, which means that only 2 of the input criteria are suitable. And we don't have a way of knowing which 2 layers are suitable. We can't distinguish. Blue is symbolizing cells where only one of the input criteria was suitable in that location, and again, we can't know which one. Gray are the areas that are wholly unsuitable. But what if the cell would be considered suitable as long as it was at a low elevation and was far from a road? Maybe slope isn't as important. How could we keep track of which cells with a value of 2 represented suitable elevations and road distances? Turns out we can do it pretty easily. Here's our reclassified suitable distance to roads layer. If we reclassify the suitable elevations as 0s and 10s instead of 1s, we can keep track of our suitable criteria in the output values. And then adding another order of magnitude for slopes, we now have a way to differentiate which cells are which in our output. So what do you think the range of output values will be if we add these three inputs together. Does that make sense? 0, 1, 10, 11, 100, 101, 110, 111. We can still manually symbolize them using green representing cells where all the input criteria are met. Dark green maps the cells where any 2 input criteria are met, and the purple maps the areas where only 1 input criteria is met. So visually, we can still simplify it. But now we know that cells with a value of 11 are secondarily suitable to cells with value of 111 because 11 represents suitable elevation and suitable distance from roads. We've found a way to differentiate and basically pull out our slope suitability. 111 maps cell locations where all 3 inputs are suitable, but 11, the value of 11 for a cell means that distance to roads and elevation are both suitable. So we could, subsequently combine those. All right, here's a challenge for you. I want you to draw this 4x4 grid that represents the output raster. Draw that out. Your inputs are elevation, distance to roads, and land cover. Each input has been classified not simply into suitable and unsuitable, but very suitable, moderately suitable, mildly suitable, and not suitable. So here we're adding another layer of complexity. Instead of just dealing with binary inputs or binary inputs, but keeping track of our variables by using orders of magnitude, now we're actually increasing our complexity from binary into a ranked classification system, from unsuitable, 0, to 3, the most suitable. We're going to add these 3 reclassified inputs together. So first, I want you to fill out the values of the output grid. If you add the upper left corners of the 3 inputs, write that value in the upper left of your output raster. That's how the raster calculator works. So you would get 303 for your value here. Write that in the upper left corner, sorry. And then keep going until you filled this output raster grid in. Pause the video if you need to. All right. Second, I want you to circle all the cells that meet all 3 criteria's most suitable habitat requirements. So circle the cells that map the locations of highest suitability for all 3 inputs. Third, I want you to tell me what cell value represents a location that has the most suitable elevation, suitable distance to roads, and unsuitable land cover. And finally, tell me what a cell value of 210 represents. Isn't this so fun? All right. Here are the cell values after adding the 3 layers together, and the circled cells meet the highest suitability for each input. 13 is the value that represents suitable distance to roads and most suitable elevation. And 210 represents cells that are moderately suitable for land cover and suitable distance from roads. All right, moving on. There are a lot of details that make this process work. And if you ignore them, or if you don't know about them, you can really blow up the fidelity and quality of your results. So the first consideration is the way the raster cells line up in space. The resolution should be the exact same for all of the input rasters, and the cell borders or edges need to align exactly in space. We can take care of all this business with a little attention to detail and a few easy steps. I'm going to include a link for a demonstration video called Preparing Rasters for Models in the description below. Make sure you check that out. It deals with the idea of cell resolution, concurrency, and orthogonality. Another thing that trips us up when combining rasters is the way we handle the unsuitable cells. It's common practice when we're classifying rasters to get rid of the data that we don't want by assigning a new value of no data. This makes the cells, in essence, disappear. And that's handy when we're trying to convert the results to polygon, because we want to limit the number of raster cells we're actually converting to a shape. So in this example, I'm taking my unsuitable distance to roads and assigning it no data, just as an example. And what you see here is that the areas that are close to a road are gone, and we're left with raster data in the areas that are far from roads, which is what we want. But the problem is when we add a raster with no data in these areas, it acts like a mask. And so the resulting output is only going to include raster data where we have data in our layers. So if we were to do this with all three, if you think about Boolean logic, it's like doing an AND. So we only want the areas of suitability in this layer and only want the areas of suitability in our other two layers. And so you'd end up with a very small output of just the areas that are intersecting all three suitability inputs. So to avoid that, it's really important to know that cells with a value of 0 can be added to other cells, but cells assigned no data will act like a mask. Okay. Let's talk about converting vector data into raster data. Let's just say one of our inputs, or more than one, is vector data. There are tools like Euclidean distance that gives us a raster with distance values, and that's a handy way to transform. You can also run tools like feature to raster, which will just convert point features into a raster where the cells, and you have to be careful with resolution here because this could be a 30-meter cell, and this is actually marking an exact XY location. So you can convert the actual features to raster cells, but typically using some kind of a buffer first on your vector data, or using the Euclidean distance tool is a good way to transform those values. The vector features can be buffered and then rasterized into binary or suitable or unsuitable regions, or you can apply multi-distance buffers, which could be rasterized to show levels of suitability. Lots of options. The next issue to keep in mind, the false exclusivity of being in or out of a polygon. We don't know that there will be animals in these polygons during the seasons. Critters aren't evenly distributed within these areas, meaning that the probability of use within the polygon area is not equal. And what about microclimates? When we think about, a winter-spring habitat and a spring-fall habitat, what about microclimates within these areas? And have these habitat characteristics changed, or will they in the future? And just so you know, I've taken this data set and used the soft light blending with no transparency over the satellite image base map. That's it. The beauty of raster modeling in a nutshell.